theory.
Good. So just to summarize what we've done so far, on Monday, we had a sort of lightning overview of some interesting features of two-dimensional conformal field theories. And then yesterday, we had a brief introduction to gravity in AdS3, and we learned that the structure of gravity and asymptotically anti-de Sitter space in 3 dimensions really shares many features with two-dimensional conformal field theories. For example, the symmetry group of the theory is the Virasoro algebra, just as it is for a 2D CFT. The states of a 3-dimensional theory of gravity look in many ways like the states of a conformal field theory. For example, empty anti-de Sitter space has an energy that, in the appropriate normalization, exactly matches the negative Casimir energy of the ground state of a conformal field theory on a circle. The heavy states in the theory were described by the BTC black hole, and the entropy of these states exactly matches the Bekenstein-Hawking entropy that we expect for a semi-classical theory of gravity in anti-de Sitter space. So inspired by these things, what I'd like to do is try and take this one step, or perhaps many steps further, to see if we can really understand exactly what we mean by quantum gravity in anti-de Sitter space. And in particular, what I'd like to do is I'd like to start by thinking about what we might hope to be the simplest possible theory of gravity in anti-de Sitter space, which I'll dub pure gravity. Sorry, did someone have a question?
Can I ask a quick question? Yes.
Yes.
Can we show that the vacuum state and the BTC black hole are the only solutions of Einstein gravity in AdS3, or like asymptotically AdS? Like, why are these two the only states that we are considering?
They are not the only states. They are not the only states. That is to say, the only solutions of general relativity with asymptotically AdS boundary conditions.
Right.
Ask me again later. One of the things that I'll prove to you, or at least state to you today, is a different sense in which they are only solutions, namely in Euclidean signature, and I'll try and use that fact. But come back to me again with that question and we can talk about it. But it turns out that there are other solutions, both singular and smooth, that obey the asymptotic AdS boundary conditions.
Okay, thanks.
Good. So, but to get back to this, let's talk about what we would expect the spectrum of pure gravity to look like. That is to say, just a theory of 3-dimensional Einstein gravity in AdS3. So it has a spectrum of states that we could briefly describe with the following picture. Sorry, my pen is not working very well. So here I'm drawing the spectrum in the energy angular momentum plane. So we have the ground state, empty AdS, which has energy minus c over 12, where I remind you that c is the central charge, which is equal to the AdS radius in Planck units. We have a bunch of black hole states which live up here in this shaded region. These correspond to the BTZ black hole we met yesterday, along with the rotating BTZ black hole. We also have a bunch of discrete states that live in this region down here. And these are the boundary gravitons. And these were obtained by taking diffeomorphisms that are non-trivial in the sense that they don't vanish at infinity, but instead act on the boundary, and using these to act on the ground state of the theory. Okay. And if we were to try and, so this is just if you like, the classical or the semi-classical spectrum of gravity in AdS3, up to some small subtlety that was asked about a minute ago that, well, I'm just going to ignore for the present. But let's ask what would happen if we try and construct a fully quantum theory of gravity. And here what I mean is a quantum theory of pure gravity, namely one that I would get by quantizing general relativity. So quantum mechanically, we would expect that the continuum of black hole states would be replaced by some sort of discrete spectrum. So in particular, there's a black hole solution for any value of the mass or the energy greater than 0. In particular, I remind you that the energy of the black hole, which in the language of CFT operators on the plane would be the scaling dimension of the corresponding operator, was given by the horizon area of the black hole. And if you plug in those formulas we used last time, it's the horizon area in units of square root g times L, where g is the Newton constant and L is the AdS radius. So there's a black hole for any positive value of E here. So there's a continuous spectrum of black holes classically, but quantum mechanically, of course, we expect that to be discretized in some way. In particular, generically, we would expect some sort of spacing of energy levels that would be like 1 over the density of states. So in particular, if these black holes obey a Bekenstein-Hawking law for their entropy, then the spacing would be exponentially close. It would be like e to the minus CE. Okay? So this, more or less, is going to be our target for today. What I want to do is I want to try and construct a theory of quantum gravity in AdS3. And I want to see if its spectrum has these properties, namely if it matches the semi-classical spectrum, but with the continuum of black hole states replaced by some sort of very, very closely spaced discretuum. So, of course, we're not quite going to succeed, but the way that we fail is going to be very interesting, and we're going to learn some lessons along the way. So to begin, how would I try and study pure gravity? Well, I would try and construct a quantum theory of gravity by doing a path integral over a space of metrics. So in particular, to proceed, what I'd like to do is try and compute the partition function. And in particular, if I'm interested in computing the spectrum, then what I should try and do is compute the finite temperature partition function. And if you want the spectrum as a function of energy and angular momentum, you should compute the partition function as a function of inverse temperature, along with a chemical potential that we're going to couple to the angular momentum. So I remind you that this is basically what we did in the first lecture in our study of conformal field theory. So we introduced a parameter that I called tau, which is a complex number that packages the temperature and angular potential. And what I want to compute is the finite temperature partition function. So trace of e to the minus beta h plus I theta j. So this is a function that's going to package the spectrum up. In the CFT language, we would call it trace of q to the L0, q bar to the L0 bar, where q is e to the 2 pi I tau. And L0 and L0 bar are h plus j and h minus j, respectively. And then if I could go ahead and compute this thing, this would give me the density of states. In particular, it would give me a density of states that I would write as some density rho that depends on E as well as on spin J. So in particular, I've written this sum as a sum over J and an integral dE because angular momentum is automatically quantized, right? That's just because of the periodicity of the angular coordinate. So we get that for free. However, the thing that we don't necessarily get for free is the quantization of energy as well. That's the target. So like in the ideal situation, for example, in an honest to God unitary compact conformal field theory, what I've called rho J of E here would be a sum of delta functions supported on the spectrum of the theory. Good. So how am I going to compute this? I'm going to remember that this is a torus partition function. So in particular, in a theory of gravity, what would this be? So this should be a sum over all three manifolds. That is to say, a sum over all metrics weighted by some Euclidean action, because the torus partition function is a Euclidean partition function on a Euclidean torus. So I'm going to try and compute this as a sum over all Euclidean three manifolds that I'm going to call M3, whose boundary is a torus. But when I say that the boundary of M3 is a torus, I have a very particular set of boundary conditions in mind. In particular, they're the Brown-Hanot boundary conditions that we discussed last time, which say that our three manifold has to approach a torus out at infinity with a specified conformal structure that's given by this tau parameter. So this is the thing that we'd like to try and compute, right? This is our attempt to really construct from first principles a theory of quantum gravity in anti-de Sitter space. Okay. Now, how would I like to try and do this path integral? Well, of course, doing path integrals in general is very hard. So usually the way that we start by doing such a path integral is in some sort of stationary phase approximation or saddle point approximation. What does that mean? That means that I'm going to try and find a set of classical solutions to our equations of motion of the theory. And then in the leading saddle point approximation, this is just going to be given by the exponential of the classical action of one of those saddle points. Okay. Now,
hi, sorry.
Yes.
This may be a bit naive, but could you repeat again why should we integrate over the manifold such that the boundary is a torus?
Well, because what I'm
why
trying
do you
to
think
do,
that would produce the correct answer?
Right. What I'm trying to do is produce the CFT partition function on a torus. And the basic statement of the AdS CFT correspond. Well, let me say that a little bit differently, actually, because I'm really not assuming any conformal field theory anywhere. I'm really trying to do a direct gravitational calculation. But remember that H here is the generator of time translations. J here is the generator of rotations. So if you were to try and construct a trace of e to the minus beta h plus I theta j, then you would be trying to do some integral over a space of geometries where t has some specified periodicity and j has some specified
so it's the trace that really gives you those two periodicities.
It's the trace, right? So remember that when you're working at finite temperature, that means that you should be in Euclidean time and that Euclidean time should be periodic. Okay.
Yes, that makes perfect sense. Thank you.
An important thing to remember here is that H is an energy that H is an operator that measures the energy as measured by some observer out at infinity. Right? But we're studying a theory of gravity. So that means that you really have to take into account fluctuations of the metric. So what does that mean? That means that you need to fix the structure at the boundary of space-time, but sum over all the geometries in the interior. Good.
Yes.
Is that clear?
Thank you. No, that makes perfect sense. Great. Thank you.
Okay. So this is how we would start by trying to compute the path integral of gravity in anti-de Sitter space. You'd start by trying to find a bunch of classical solutions. And then, if you're very, very powerful, you would start computing loop corrections to these classical solutions. Okay. Now, how would I organize this? Sorry, did someone say something?
Can I ask a very naive question?
Yeah.
Which is, why do we expect to necessarily to have a discrete spectrum for black holes? Can't we have like continuous spectrums of energies in this case?
Remember that gravity in AdS is like gravity in a box. Any quantum system in a box of finite size will have a discrete spectrum. Take a black hole, put it in a box, and quantize it. It better have a discrete spectrum just like everything else. Okay. And what is the density of states? The density of states should be given by the Bekenstein-Hawking formula, right? The Bekenstein-Hawking formula, if you interpret black hole entropy statistically, is saying that black holes microscopically have a finite density of states. Right? So that means that the continuous, continuous spectrum classically should be replaced by some discrete spectrum quantum mechanically. Good. Any other questions? Yeah. Good. Okay. So what that means is that what I'd like to do is try and see if I can go just beyond a classical approximation and compute subleading quantum corrections to this path integral. So how am I going to organize this? Well, I want you to remember that the central charge of the theory, 3L over 2G, if I were to restore my factors of H bar, that thing goes like 1 over H bar. So that
can I ask you a question about the last part?
Yes.
Mm-hmm. You said this quantization condition where a theory in a box gives you a finite spectrum, a discrete spectrum. I can see how that works for massless particles, but massive particles don't actually see the box. How do you show that for massive particles, this quantization still holds?
So
I mean, a massive particle never reaches the edge of the box. Yeah.
That's right, because AdS is like having a gravitational potential that confines particles to be in a region of finite size. So if you're in a region of finite size, then you're like being in a box, right? I mean, AdS is not exactly a box. That's an analogy, not a rigorously mathematically precise statement. If you have a particle of energy E, it's like being in a box whose size scales with E in some way that I can't remember off of the top of my head. But if you just, okay, exercise, right? Quantize a massive particle in AdS and see if the spectrum is discrete or continuous. Remember, if you're going to have to be careful. You have to do it in global coordinates. If you do it in Poincare coordinates, you'll get a continuous answer. But that's only because you've thrown out a point at infinity. If you do it in global coordinates, you'll get a discrete spectrum.
Nice. Okay, thanks.
Good. Great. I mean, there's one caveat. If you've got some funny kinds of matter, like long strings or something like that, that can go out to the boundary with only a finite cost of energy, not an infinite cost of energy, then you could have things like continuous pieces of the spectrum. But let's just not worry about that for now. Okay. So how would I like to go about trying to compute the path integral of gravity in AdS? Well, I have this classical action. So the classical piece goes like 1 over H bar. So I'm going to explicitly pull out a factor of C here out front, because that's going to be proportional to C. So that's going to be the classical action. Then if I'm very powerful, there'll be a 1-loop correction that I could compute. And if I'm even more powerful, then I should be able to compute a 2-loop correction, a 3-loop correction, and so on and so forth. Okay. And then this, at least in principle, is an expression for the partition function that includes contributions from all of the classical geometries, which we would refer to as all of the instantons. That's the name we give to a solution of the Euclidean equations of motion, as well as all of the loop corrections. And to the extent that we can make quantum field theory path integrals precise, what we mean by the full quantum field theory path integral is that it is equal to the sum over classical saddle points, each dressed by a series of quantum corrections. Okay. Now, I'm being a little bit sneaky here, and so I'll discuss this at the end if I have time. There might be cases where there are other sorts of contributions, but for now, let me just take this as my goal for what I want to try and compute. So I'm going to compute a path integral of general relativity in AdS, and I'm going to do it by finding an infinite series of geometries, all of which contribute to the path integral, as well as the infinite series of perturbative corrections, what we would call Feynman diagram corrections. it turns out that we can find all of the classical solutions and compute all of the perturbative corrections around each classical solution. And if you think very, very carefully, I've already told you the answers to both of those questions. I just haven't told you that I've told you them. Okay. Good. So let's try and understand how that works. Okay. So first of all, let's talk about what sort of classical geometries would contribute to the finite temperature partition function of gravity in AdS. So one simple contribution would just come from empty anti-de Sitter space itself. So in particular, one of the geometries which contributes is just empty anti-de Sitter space. So let me remind you of what the metric of empty anti-de Sitter space was. Here I'm going to set the AdS radius equal to 1 just so that I can write the metric a little more simply. So this is the metric of AdS in global coordinates in Euclidean signature. So I've called t here my Euclidean time coordinate. Now, phi here is a periodic variable with period 2 pi. But I'm trying to compute the partition function on the torus. That is to say, I'm trying to compute the thing at finite temperature. So what that means is that I also need to periodically identify in Euclidean time with period beta. Okay. There's no reason I can't do that. You know, t here is a killing vector, so I could always just periodically identify in Euclidean time. Good. So this geometry has a name, okay, because it's not just AdS, it's the thing that we might call thermal AdS, which is to say it is the geometry that you would use if you wanted to study perturbative quantum field theory in AdS at finite temperature. Okay. If I were to try and draw a picture of this geometry, I would draw it as a solid donut. Okay. Why am I drawing it as a solid donut? Well, its boundary is a torus. But if you think about it, the full three-dimensional geometry is going to be a donut because AdS is like a solid cylinder. But if I periodically identify in Euclidean time, I'm gluing together the top and the bottom of that cylinder to get a solid donut. And the way I'm going to draw it is as follows. So here phi is this circle that goes around one side of the donut, and the Euclidean time direction goes in the other. Okay.
Sorry, can you explain one more time why you periodically identified the Euclidean time? Because I feel like that was an important step.
So I'm just doing the same thing that we always do when we study thermal physics. So in thermal physics, if you want to compute the thermal partition function of any system, what do? You go to Euclidean signature and you periodically identify in Euclidean time. Why is that the right thing to do? It's because e to the I ht is the time evolution operator in Lorentzian signature, which if you do a Euclidean, if you do a change of coordinates to go to Euclidean space, will become e to the minus ht, okay? And so the operator e to the minus beta h is one that implements a translation by an amount beta in the Euclidean time direction. And then the operation of a trace is an instruction to glue the geometry at t Euclidean equal to 0 to the geometry at t Euclidean equal to beta. That's a great, exercise. Convince yourself of this for a single particle in quantum mechanics, that the path integral definition of quantum mechanics for a single particle allows you to compute the thermal partition function of a particle moving in a potential by going to Euclidean signature and periodically identifying in Euclidean time. That's a great exercise to do. Without all of the sort of fancy rigmarole of quantum field theory, you can sort of convince yourself of this rather easily if it's not obvious already. Great. Good. So this is one geometry that contributes to the path integral. Okay, so we're already in business. It turns out that there are other geometries that contribute to the path integral of gravity on a torus. So in particular, there's another geometry and this geometry is going to be the one where I just do a change of coordinates, where I swap what I call the angular coordinate phi and the Euclidean time coordinate t. So in particular, if I just do that change of coordinates, then you get a geometry that looks like this. Okay? So what have I done? I've done the diffeomorphism that interchanges phi with Euclidean time. Right? Now, because this geometry is related to the one I wrote down above by a change of coordinates, you might think that this doesn't give a new contribution to the path integral of general relativity, right? Because two metrics related by a diffeomorphism are supposed to be the same. But remember, I spent all of the lecture yesterday yelling at you about the definition of gravity in anti-de Sitter space being that diffeomorphisms that don't vanish at infinity are not regarded as gauge transformations. So in particular, this should be regarded as a new solution of general relativity, even though it's the same geometry, because I've done a diffeomorphism that acts non-trivially at the boundary. And in fact, you've met this geometry before. So in particular, exercise show that this geometry is the Euclidean BTZ black hole. Okay. Now, how do you know that this is a black hole? Well, first I'll give you a hint. So hint, let's just remember that the radial coordinate is supposed to be the coefficient of d phi squared. So that means that you're going to need to do a diffeomorphism where you replace r by 1 plus r squared, or r squared by 1 plus r squared. Okay? Do that diffeomorphism, and it's straightforward to check that this is Euclidean BTZ. If you're bored, you could do it right now while I'm lecturing. What's another way of immediately seeing that this is a black hole geometry? Well, if I wanted to draw a picture of this geometry, then it's going to be a solid donut, but it's going to be the solid donut where the Euclidean time circle has been swapped with the phi circle. Okay? So what does this picture mean? It means that this is a geometry where the Euclidean time circle is contractible. In other words, there is a place in the geometry where the coefficient of dt squared is equal to 0. Now, we have a name for places in the geometry where the coefficient of dt squared goes to 0. We call those event horizons, right? That's the definition of an event horizon in Lorentzian signature. So the point is that the thing that was the origin of the polar coordinate system in thermal AdS has become the event horizon of this black hole. Now, let's go ahead and investigate this geometry in a little bit more detail. So in particular, we have some periodicity conditions that t and phi are going to obey. So in particular, they're just going to be these same periodicity conditions that I wrote up here, but with t and phi switched. So in particular, phi is going to be periodic with period beta, and t is going to be periodic with period 2 pi. Or if I did a scale transformation, because remember, I only ever care about the conformal structure of the boundary. So I can always rescale, do a change of coordinates, if you like, to rescale my coordinates by an amount that I like. So if I did a change of coordinates, this would identify phi with period 2 pi and t with period 4 pi squared over beta. Just rescaling both coordinates by a factor of 2 pi over beta. Why is that the right thing to do? That's the right thing to do because what I want to do is, if I want to compare this top geometry to this bottom geometry, then I should do so by making sure the size of my circle is the same. You know, I want to identify phi with period 2 pi in both cases. Now, if you remember back to the first lecture, we already met a symmetry of conformal field theories that takes beta to 4 pi squared over beta. That is to say, it takes temperature to 1 over temperature. That was the modular transformation. So what we now conclude is that Euclidean BTZ is related to thermal AdS by a modular transformation So in the boundary CFT language, we would call it a modular transformation. But in the bulk, we would call this a diffeomorphism. That is a change of coordinates that doesn't vanish at infinity. Okay. Good. Now, I remind you that the modular transformation that takes beta to 4 pi squared over beta was just one of an infinite set of modular transformations. Okay. And in particular, we could, in fact, do any SL2Z modular transformation.
Sorry, yesterday you
To
said
obtain
that
a new geometry. Sorry, did someone say something?
Yeah, I had a question. Yesterday you said that the diffeomorphisms that don't vanish at infinity are the conformal transformations on the boundary.
Yes.
But then modular transformation is not a conformal transformation. So
it is a conformal transformation. It is not a conformal transformation that is continuously connected to the trivial one. It is a conformal transformation of the torus that does something fancy to the torus. In particular, how should you think about it? You should think of a torus as having two non-contractible cycles, and an SL2Z modular transformation is some mixing up of those different cycles. Okay. In particular, if you think of the cycles as I've drawn them here as a time circle and a phi circle, it interchanges the two. But in a general modular transformation, we'll act on those two cycles with an arbitrary SL2Z matrix.
Okay.
So in particular, the way that we presented it on Monday was that a general SL2Z transformation was given by a set of identifications on the complex plane. So here I'm thinking of Z as a complex coordinate on my boundary. And for any complex parameter tau, any modular parameter tau, you can define a torus. And one of the things, you know, where you identify Z with Z plus 1 and Z plus tau. And one of the things that we observed on Monday is that just by acting with an SL2Z matrix here, namely a 2x2 matrix with integer entries that is invertible, all that is, from the boundary point of view, is just a relabeling of the different cycles on the boundary torus by the multiplication by this SL2Z matrix. But you can also think of this as changing the tau parameter. So that takes tau to A tau plus B over C tau plus D. And this expression that we obtained up here, where T Euclidean is identified with period 4 pi squared over beta, was just a simple example of this, namely the one where tau goes to -1 over tau which is to say the SL2Z matrix would be 0, 1, minus 1, 0, okay? Which is an integer, an invertible matrix with integer entries. Good. So in particular, what we see is that there are an infinite number of possible geometries that we can construct that are obtained by doing a coordinate transformation that mixes up the space and the time directions. The Euclidean circle that defines the angular coordinate and the Euclidean time circle. Okay. So there's one final subtlety in the story, which I'll just mention to you as an aside and an exercise for those who are interested, which is that the modular transformation that you usually call T, the one that just takes tau to tau plus 1, does not actually give a new geometry. So in particular, for those of you who've studied modular transformations before, you may remember that SL2Z is generated by a matrix T that I've written here, and another matrix usually called S that I've written here. SL2Z is an infinite group generated by the S and T matrices. It turns out that only S, so T does not give a new geometry, but S does. Okay? And so, in fact, what that means is that there are an infinite number of geometries labeled by SL2Z mod Z, where Z is generated by those transformations that take tau to tau plus n, or tau to tau plus 1.
Hey, could I ask a question about your exercise?
Sure.
So I can do it afterwards. This group element would act on a vector of TE and phi. Is that right? It's a coordinate transformation on TE and phi. Okay, great. Thank you.
Good.
Can I ask another question?
In the language, for those of you who've studied geometry, this is known as a Dane twist. I don't know if those words are exciting to anyone. Yes, but there's a question.
Oh yeah, just the infinite number of geometries that you get by these SL2Z transformations, are they also black holes? Like, will they?
Yes, well, they're Euclidean solutions.
Mm-hmm.
So
those are all the instantons.
They're what we would usually call instantons.
Okay.
So exercise, show that they can be obtained as, actually it's not so bad, show that these can be obtained by Euclidean continuation of the rotating BTZ black holes. Okay.
Okay. So will they have a coefficient of dt squared that?
They will have a coefficient, as with any rotating black hole, the metric will no longer be diagonal. There'll be fancy things that mix T and phi. The one subtlety here is that whenever you go to Euclidean signature for a rotating black hole, you have to take angular momentum to I times angular momentum in order to get a real solution. That's because angular momentum is a pseudo vector instead of a vector. So it picks up an I when you go to Euclidean signature. This is this standard Gibbons-Hawking procedure. So one final, yeah.
Just one question. In that exercise, what do you mean by does not give a new geometry? Do you mean that the diffeomorphism vanishes at infinity?
Let me say it a different way. Okay. So another way of characterizing these geometries. So the geometries are characterized by a choice of cycle in the boundary torus, which is made contractible in the bulk. So in particular, let's imagine a torus a little bit more abstractly. So we've got two cycles. We could call one of them Euclidean time and one of them the angular cycle. So I've drawn two geometries above, one where phi is contractible and one where t is contractible. But you could always take any linear combination of them and choose that to be contractible. In particular, you could choose any coprime integers, c and d, and make the cycle ct plus d phi contractible. So for example, if c is equal to 2 and d is equal to 1, that would be a cycle that looks a little bit like this. That would be contractible in the interior. Okay. Final exercise. Show that SL2Z mod z is parameterized uniquely by a coprime pair of integers c and d. And in fact, I've called them C and D because they're the lower row of an SL2Z matrix. Good.
So the idea is that if it would be an SL2Z that would be coming from that T matrix, then it would not change which cycle.
Exactly.
And therefore it is an actual diffeomorphism.
Exactly. Yeah.
Okay.
Good. Okay. Now I'm just going to quote a mathematical fact to you.
Excuse me, can I ask one more question? So all these geometries that we generate by SL to Z by Z transformations, they're all saddle points that contribute to the path integral, right?
Mm-hmm.
Okay, so we have an infinite number of, and could we just find all these solutions just technically by solving Einstein equations? Or
Yes. Yes, but you have to be a little careful, because if you didn't remember Brown and Hanot, you would think that there's only one solution, right? Because remember, the geometry of all of these is the same, right? These metrics are all related by diffeomorphisms. They just happen to be diffeomorphisms that don't vanish at infinity. So such geometries where you specify a three-manifold by taking a surface and filling in the surface are known as handle bodies. And it's a fact that the handle bodies that I've described above, namely this family of geometries parameterized by C and D, are the only smooth solutions of general relativity whose boundary is a torus. Good. Okay.
Ask something.
Yes.
At the level of solutions, wouldn't things that are closed three manifolds without boundary and disconnected from this also be solutions?
Yes.
I mean, I guess they would become vacuum bubbles, but
exactly. So remember that when we define a theory, we need to specify our boundary conditions. Here, my boundary conditions are specified by the fact that I have a torus at the boundary. You could always imagine adding completely disconnected things, but indeed, these would be interpreted as vacuum bubbles. Okay.
Yeah.
Yes, if you like, you would discard them the exact same way that we discard vacuum bubbles in quantum field theory. Namely, we attribute these to some normalization of the cosmological constant.
All right, thank you.
Good. If you like, you could say very fancy words like the central charge that I'm working with is a renormalized central charge, or the AdS radius that I'm working with is a renormalized AdS radius, where I've already subtracted all of these things off. There may be something subtle there, okay, but let's just move along for now.
Okay. Sorry,
Good.
I have a question.
Yes.
Is there, like, do we have a justification for not including non-smooth solutions, or?
Right now, I am following my nose and trying to define the path integral of gravity as a sum over smooth geometries. It turns out the answer I'm going to get does not make sense. And one possible resolution of that is to include non-smooth geometries, which we will get to.
Okay, good. Thanks.
Good. Okay. Now, what about the quantum corrections? Okay. So let's now, in fact, I've already given you all the tools you need to compute the infinite series of quantum corrections. That is to say, the infinite set of Feynman diagrams that contribute to the action of one of these solutions. Okay. So in particular, let's remember that thermal AD, that one of the geometries that I wrote down is what we would call thermal AdS. So in particular, that's the geometry that you would use to compute partition functions of quantum fields in a fixed AdS background. Now we're trying to study pure gravity, right? So there's no quantum fields. So you might think that there's nothing really to do here, except we have to remember that our theory does contain gravitons. They're just these things that we called boundary gravitons. Okay. So in particular, what is the partition function of thermal AdS? So by definition, this is the thermal partition function of all of the perturbative states propagating in anti-de Sitter space. So we might call that the vacuum Hilbert space. And it's going to be the trace of Q to the L0, Q bar to the L0 bar over that space. Okay. And what is this space? Well, it's going to include the ground state, of course. That's empty anti-de Sitter space. But it's also going to include all of the descendants of the ground state. These are the analog of the perturbative gravitons in the theory. So it's going to include stuff like L minus 1 to some power, all the way up to L minus K to some power, acting on the ground state. So these are the things that we discovered on our lecture on Monday. These are the descendant states that always exist in any conformal field theory. And indeed, we discovered they will always exist in any theory of gravity in AdS3. Where here you think of the L's as the Virasoro generators built out of the local diffeomorphisms that don't vanish at the asymptotic boundary of AdS3. Now, what is the trace over H over this set of descendants of Q to the L0, Q bar to the L0 bar? Well, first of all, we have the contribution of the ground state. So the ground state has energy minus C over 12, which means that L0 plus L0 bar is minus C over 12. And the ground state also has spin 0. So L0 minus L0 bar is 0. So the contribution from the ground state will just be Q to the minus C over 24, Q bar to the minus C over 24. And what do these Virasoro generators do? Well, L minus 1 is going to raise the energy of the ground state by 1. L minus 2 raises the energy of the ground state by 2, and so on and so forth. Okay. So what do these do? They act like a bunch of harmonic oscillators. Okay. Right? Because each L minus K is just like a simple harmonic oscillator raising operator with energy K. So you're going to have a product over all of these Virasoro, all of these different possible Virasoro raising operators of the partition function of a simple harmonic oscillator of energy n, along with an analogous expression for the Q bars if I act with a bunch of the L bar raising operators. And there's one final subtlety here, which is that we have to remember that the AdS ground state is SL2R invariant, meaning that it's annihilated by L minus 1, which means that this thing that I called N1 better be equal to 0, or else you're going to get 0. So in fact, this is a product starting at n equals 2, going up to infinity, not n equals 1. Okay. So let's stare at this for a second. And let's remember what this is supposed to be. This is supposed to be the contribution to the path integral coming from geometries that are thermal AdS or nearly thermal AdS. To say it a little more fancily, this is the contribution coming from the integral over metrics that are continuously connected to thermal AdS, which we, in the language of quantum perturbation theory, would write as a classical action, which would be proportional to C, and a one-loop action, a two-loop action, and so on and so forth. Okay. So here, this quantity that I've computed here has a name. We would call it a character of the Virasoro algebra, right? That's the group theory name for the function that counts the spectrum of the theory. And so we conclude that the Virasoro vacuum character is the perturbative expansion of general relativity, the general relativity partition function in AdS. And in particular, you can see that the classical action is q to the minus c over 24, absolute value squared. The one loop action is this product. And all of the higher loop terms vanish. So we conclude that the path integral of general relativity in AdS with these boundary conditions is one loop exact. Now, this is an incredibly slick argument. You can also be much more straightforward. So for example, S naught is a classical action. You could just go ahead and compute the classical action of thermal AdS if you like. Okay, there's a little subtlety because it's divergent, because AdS has infinite volume. You need to introduce what we call boundary counter terms. You adjust those appropriately, and you get the answer exactly as I described. You can also do a one loop calculation in AdS. How would you do that? Well, we're studying a quantum field theory. You know how to do one loop calculations. It's a little hard because it's a quantum field theory in curved space, and we're studying gravity, which is a gauge theory, which means there's a Fadeev-Popov determinant involving ghosts. It's a computation. It's not easy, but you can do it, and you can check that you get this answer. In principle, we could even do the higher loop calculations. I don't know anyone who's brave enough to do it. Maybe one of you are, but in principle, you should be able to calculate the two-loop effective action of general relativity in AdS with the appropriate boundary conditions in 3 dimensions and see that it's exactly 0. Okay, that would be a great calculation to do, but it's a hard one. And I think nobody has bothered to do it because we know that the answer is 0.
Sorry, can I ask a question?
Yes.
Well, is there any other way to just figure I guess the fact that this result is one loop exact is very surprising. Is there any other way that you can just see it from basic principles or AdS3?
So that's a good question. To some extent, yeah. Whether you consider whether you consider this a distinct argument or not is in the eye of the beholder. There are arguments based on localization. So, Witten has a beautiful paper from the 80s on the quantization of the coadjoint orbits of diff S1. So what is diff S1? In the present context, diff S1 is a space of diffeomorphisms of the circle. We think of those as being part of the space of diffeomorphism, the space of diffeomorphisms that don't vanish at infinity. So remember, the non-pure gauge diffeomorphisms were the ones that don't vanish at infinity. And there's, in fact, a set of beautiful arguments that are a bit more mathematical that allow one to directly quantize diff S1. Diff S1 is a group manifold, so you can just quantize it. You can think of it as a phase space and quantize it just as you would any other quantum mechanical theory. And you show that you get representations whose characters are exactly the characters of a 2D CFT. So that, whether you consider that an independent argument from the one I have given here, I'm not sure. There are other arguments based on localization. You know, localization is the tried and true way of proving one loop exactness in a quantum field theory. Again, the localization arguments all kind of boil down to the same thing. So I don't know if you consider these independent arguments or not. Okay. In general, I think it would be great if someone wanted to roll up their sleeves and do a 2-loop calculation of gravity in AdS3. If you look in detail at how the 1-loop calculation is done, you know, it might sound like a good idea, but then you'll read the details of the 1-loop calculation and change your mind, because it's not actually very easy. But I don't want to discourage anyone. Okay, exercise. Check S2 is equal to 0 directly. Email me if you do this when you do this exercise. Okay, good.
I have a simpler question. I'm just confused. We're not done, are we? Like, don't we still have to include the contributions from like the Euclidean BTZ black hole and all of the? Yep. Oh, okay. This is just like one piece of it, right?
This is one piece.
Okay.
Good. But we're pretty close to done, because all those other pieces are related by modular transformations. Okay. So in particular, the partition function of general relativity is as a function of inverse temperature, that is to say, as a function of this modular parameter tau. Well, we have to sum over all these geometries labeled by this coset. Okay. One of the contributions is this thermal AdS answer. And all of the other ones are related to it by modular transformations. So remember, if gamma is ABCD, then gamma tau is defined to be A tau plus B over C tau plus D. Okay. Let's think about it, right? Because, you know, Euclidean BTZ was just related to thermal AdS by a change of coordinates. So if I know the classical action and the 1-loop action and so forth of thermal AdS, I know it for BTZ. Okay. So sums of this. So this is a kind of sum. A sum over the modular group has a name. We usually call it a Poincare series or a Poincare sum. Sometimes these are also known as Eisenstein series. So this is a kind of Eisenstein series, if you've encountered those. It's not the kind that you'll see in a math book necessarily, unless you're looking at the right math book. One important feature of this sum is the sum diverges, but it can be regulated. Okay. I'm not going to go through the details. So in fact, checking that the sum diverges is a easy and interesting thing to do. Maybe in the interest of time, well, when I write up these lectures into lecture notes, I'll include an exercise. Okay, exercise, check the sum diverges. Actually regulating the sum is a little harder. You use zeta function regularization and stuff like that, but you get a finite answer at the end of the day. And that answer is an answer for the spectrum. Okay. So what does the answer look like? Well, the answer looks very close to the one that I presented at the beginning. So it's got a vacuum state. Unfortunately, the density of states is still continuous, And even worse, it's negative. So in particular, there's a certain piece, like if E is very close to J, where the density of states is negative. So there's two problems here. So one problem is that it is a continuous density of states. And the other problem is that there are places where it's negative. So at the time when this was discovered, 11 or 12 or 13 years ago, the continuous density of states was regarded as a problem. Okay. It still might be a problem. But nowadays, we interpret the continuous density of states differently. We interpret it in terms of averaging over quantum field theories, ensembles of quantum field theories. You say words like chaos and wormholes and stuff like that. That's what I'm going to talk about tomorrow. Today, I'd just like to talk about the negativity, okay, and how we should think about the negative density of states.
Wait, I'm really confused. I thought this was the whole point, that we were going to do this and find that the spectrum was discrete.
Well, good. So our goal was to try and find that the spectrum was discrete. How do we interpret the fact that it is not discrete? Okay. One interpretation, which is what we're going to spend the whole lecture tomorrow on, is that pure gravity is not dual to a conformal field theory, but rather it is dual to an ensemble of conformal field theories. This will turn, and then the fact that the spectrum is continuous is interpreted as a consequence of the fact that pure gravity is not dual to a conformal field theory, but instead emerges when we average over many conformal field theories. So nowadays, and I think this is still something where the jury is out on whether that is exactly the right interpretation. So perhaps the continuum appears because gravity emerges as an average over many CFTs. But in order for that to be a good interpretation of the theory, we better do something about this negativity. Right? Because it's certainly possible to average a bunch of discrete densities to get a continuous density, but that density will always be positive. To say this another way, the average of positive numbers is a positive number. Okay. So in order for us to even hope for an interpretation in terms of an average over CFTs, we need to think about this fact that the density of states is negative. So what about the negativity? Okay. So in order to cure this negativity, we must include something else in the path integral. And here is a place where nobody quite knows what the right answer is. Okay, so I'm going to present three possibilities. So this is one possibility that was, so here, this is one possibility, which is that perhaps we should really sum over two copies of SL2Z, that is to say, complex metrics. So in particular, when I was trying to do the path integral of general relativity, implicitly, I was imagining integrating over real metrics. But, no, who cares about Euclidean path integrals? We only care about Lorentzian physics. And so when you go from Lorentzian time to Euclidean time, you're doing a contour rotation. Perhaps when we do this contour rotation, you should really think about picking up contributions from complex geometries. In order to make this precise, you would really need to understand what the contour of integration of the path integral of quantum gravity means. Nobody really understands that, but there is a very natural guess for the kinds of things that might contribute. So in particular, we computed the sum over SL2Z of this vacuum character. That is to say, the thing that counted the density of states in thermal AdS squared. Okay. But what if we made the most gentle possible modification of this and moved the absolute value sign just 1 centimeter over? Okay. What happens then? This is now a double sum over 2 copies of SL2Z, each which act on the holomorphic and anti-holomorphic thing separately. So now by hand, I've added in an infinite number of saddle points. But remarkably, this solves both of the problems I described above. So here, now, the things that would be contributing to the sum over geometry include what we would call complex metrics. But in
where
fact,
does this appear in the, oh, sorry, where does this proposal appear in the literature?
This is Witten's original, okay. Part of this appears in Witten's original paper on 3D gravity reconsidered. Part of it appears in my subsequent paper with Witten in 2007. Other papers, there's a paper by Jan Manscott, a paper by Shi Yin. There was an entire literature on so-called topologically massive gravity, which pursued this idea in a great deal of detail. This particular sum in that context was in a paper that I wrote with Andy Strominger and Wei Song. But I can, yeah, there are more. So there's a long literature here, but the starting point really is the paper of Witten on 3D gravity reconsidered. And then we had some comments on that in the follow-up that I wrote with him the following year. But let me just, so to some extent, sorry,
Alex,
there's a weird circle. Yes.
Alex, just to let you know, you have 5 minutes.
Okay, awesome, thanks, good. So let me give you an example of what the answer looks like, okay? So this gives candidate partition functions which holomorphically factorize. So in particular, they give what are known as the so-called extremal CFT partition functions. So for example, let me tell you what they look like, okay? So they have a central charge, which is a multiple of 24. And all of the dimensions of operators, that is to say, all of the energies of states in these theories, are integrally quantized. Okay. So this is very different from what you would expect in a generic CFT. In a generic CFT, the central charge could be some random number, but it's certainly not a multiple of 24. And dimensions are general real numbers, not necessarily integrally quantized. Exercise show that in any chiral CFT, that is to say a CFT whose partition function is a holomorphic or a meromorphic function of tau, the central charge is a multiple of 24 and The energies are integers. Okay. Energies being integers is easy. Central charge being a multiple of 24 is less easy. But let me just give you an example of one. The simplest one, when C is equal to 24, is a theory whose partition function, and I'll just write down the holomorphic part of it, not the anti-holomorphic part, is Q inverse plus 196,884 times Q plus so on and so forth. Okay. How do you think about this? This is supposed to be a partition function that counts states in the theory. So what's being counted here? Okay. Remember, the ground state has energy C over 24 on the holomorphic side and C over 24 on the anti-holomorphic side. So there's a coefficient 1 here, which is the number of ground states. So that 1 here is empty AdS. What is this 196,884? Well, 196,884, through very complicated mathematics, is 196,883 plus 1. Okay. And here, those 196,884, that's counting the number of states of dimension 2 in the theory. And there's one state of dimension 2, which is L minus 2 acting on the vacuum. That's what we would call a boundary graviton. And then we have a bunch of other states, and these are what you would identify as black holes. Okay. You could even look at the analog of the Bekenstein-Hawking formula in this theory. And the analog of the Bekenstein-Hawking formula is the statement that 196,883 is e to the 4 pi, which exercise, put it in your calculator and check. And it's pretty close. It's within 98% of being true. And you can even include a one loop correction, and it gets much, much better. You can even include higher terms. The most remarkable thing about this is that the CFT exists and is known. It has a name. It is the monster CFT. 196,883 is an interesting number because it is the dimension of the smallest non-trivial representation of the monster group. So one possibility is that other complex geometry should be included in the path integral of general relativity. And the result would be that you get one of this, a special kind of CFT, of which the monster CFT is the first example. Okay. People spend a great deal of time, however, looking for other CFTs with larger values of the central charge. Nobody has found them yet. That does not mean that they do not exist.
Can I ask a question about these?
Yeah.
Does such a CFT necessarily have a gap up to the black hole operators?
Yes. That is practically the definition of the CFT.
I see.
Yeah.
Okay.
Good. Good. I mean, there's been a great deal of discussion in the literature about whether these ECFTs exist for higher values of the central charge. I'll say that the construction of these things is based on lattices. At least the monster CFT is based on lattices. And the space of lattices is wildly interesting, but also wildly difficult to study. So for example, the monster CFT is based on an even self-dual lattice of dimension 24, of which there are 72. Okay, 72 is a number. You can write a paper on 72 different things and it'll be a paper of finite size. If you wanted to try and study lattices of dimension 48, the number of lattices of dimension 48 is bounded below by 10 to the 120. You cannot write a paper of finite size with 10 to 120 different lattices. So the construction of these extremal CFTs is presumably a very difficult mathematical task. Let me just mention, I'm just about out of time, but let me just mention that there are two other proposals out there for ways that we could fix up the partition function of pure gravity. So another proposal is to include singular geometries, in particular to include orbifolds. So in particular, I don't think I will have time to discuss it, but there is a very interesting calculation you can do, where if you study the partition function of 3D gravity, and you allow yourself precisely Zn orbifolds, then these will be extra states that live right here. And this, it turns out, will magically fix up the negativity in the partition function. Doesn't get rid of the continuum, but it fixes up the negativity. So that's one more possible avenue, things that you could do to fix up this calculation of the path integral of pure gravity. But a final proposal would be to include geometries, that is to say, contributions to the path integral, which are far from classical solutions, in particular, which are not connected smoothly to solutions of the equations of motion. So this was discussed, for example, in a paper last year by Maxfield and Turiachi. The motivation here comes from analogous computations in one less dimensions, where people have studied JT gravity. I imagine this is what Phil and Steve will be talking about next week, at least to some extent. And in that case, it turns out that one can study the path integral, a very closely connected path integral to that of 3D gravity in 2 dimensions. And it turns out that there's a way of studying this path integral where one can even include the geometries that are not continuously connected to solutions. So perhaps the same thing is true here. And this may fix up the negativity. Unfortunately, at this point, I don't know of any calculation of the full spectrum that one would get out of this proposal. Okay, that's something that doesn't seem to have been done. But that, I think, is another way out. So I think maybe that's a good place for me to end. There's a lot more that we could say, but maybe in the interest of time, I'll just stop here. And then tomorrow, we'll kind of move on to maybe the modern interpretation of this in terms of AdS gravity as an average over conformal field theories. So, but I'm happy to take questions if there are any questions.
Thank you.
Ask a question. If the monstrous CFT solves both of the problems, why did the story not end there?
Good. So good question. So the problem is that, well, okay, like I'm trying to summarize, about a decade's worth of discussion in the literature in a few minutes here. There was a great deal of there were a lot of attempts to construct extremal CFT partition functions with larger values of the central charge that went nowhere. What you can do is you could try and construct other extremal CFTs analogous to the monster CFT based on lattices, but you can actually show that such a construction will eventually fail at sufficiently large values of the central charge. That doesn't mean that they don't exist. It just means that they're difficult to construct. So for example, even at c = 48, there are over 10 to the 120 different lattices. And so the actual construction of an extremal CFT seems like it would be a very tall order. So I think, so one reason why people stopped pursuing this is that if the goal was to try and construct explicitly a conformal field theory dual to pure gravity, then the construction of these extremal CFTs seemed too difficult for us to try and handle directly. But I think there's another probably more important reason not to consider this quite as seriously. Well, one such reason is that, I did something pretty ad hoc here, which is where I declared that I was going to sum over 2 copies of SL2Z rather than 1. And that means that I would, roughly speaking, need to consider complex geometries. There is a way around this. What you could do is you could study what people call topologically massive gravity, which is a theory that is, or I should say more properly, chiral gravity, which is a theory of gravity that is holomorphic on its own. And in that case, you're really only summing over 1 copy of SL2Z. So that seems like something that's, pretty easy to understand. I think the real reason why people haven't taken this, what people don't consider the story complete here, is that there is a sense in which any chiral CFT is trivial, okay? In the following sense. So in a chiral CFT, you've got every operator in the theory is chiral. And chiral operators correspond to conserved currents in 2-dimensional CFTs. So for example, you're all familiar with the stress tensor, which is a chiral operator. And the statement that it's a holomorphic function is the statement that it is a conserved current, okay? And so in a chiral theory, every operator in the theory is a conserved current. So what that means is that this is a theory that has a ginormous symmetry group, okay? So that is way, way, way bigger than the Virasoro algebra. So if you like, you should think about every chiral CFT as a theory where you have lots and lots of states in the theory only because you have a huge number of symmetry generators. Okay? And in particular, in the same way that this 1 here is a descendant of the vacuum state under the Virasoro algebra, in fact, the 196,883 other states are also descendants of the vacuum, but under a much fancier algebra, okay? An algebra that involves the monster group. And so, in a sense, so what that means is that chiral theories are all integrable theories in the same sense that the rational conformal field theories like the Ising model are integrable theories. So if we're interested in 3D gravity as a model for higher dimensional gravity is almost certainly not an integrable theory, right? Except in very, very special limits. And so these extremal CFTs and chiral CFTs are all incredibly integrable. And so because of that, even if you interpret these as, if you interpret the monster CFT as a theory of gravity, it has a set of states that obeys something that looks like the Bekenstein-Hawking formula, but these don't really look like black holes in all of the other ways that you would like black holes to look in a more complicated theory of gravity. So there's one way in which that's abundantly clear, right? So in particular, in a generic theory, you expect the level spacing to go like 1 over the density of states, right? That's a very fancy way of saying that in a generic theory, the states are non-degenerate, right? So, in a typical theory, if you've got a bunch of states, then they're all going to be individual energy levels with some splitting that might be small but non-zero. Instead, in the theory that we're looking at here, we have delta E is order 1. It's not just order 1, it's equal to 1. Okay, but that's also order 1. And so what that means is that rather than having a bunch of different states that are very closely spaced, you have a lot of states, 196,884 of them that are all sitting right on top of each other. And that's a symptom of the fact that this is an integrable theory. Okay. And so to some extent, I think that if our goal is to find a model of three-dimensional gravity that is as solvable as possible, then these extremal CFTs are really great candidates. But if your goal is to find something that looks as much as possible like, the full glory of gravity in higher dimensions, then I don't think you would want to focus on chiral CFTs. You would want to focus on things that have more complicated dynamics. Okay. Good. Yeah, so sorry, that's my attempt to summarize many years worth of discussion in the literature in a few minutes. Yeah. But I think it is an interesting open question as to whether these things exist, right, as CFTs.
Pure gravity also has no moduli, right? You can't vary things around. It's kind of one fixed theory sitting at one point. And
that's right. That's right. Right. I mean, CFT, yeah, there are no marginal operators in a chiral theory. So, there's nothing, yeah, there's no moduli. But I mean, generic conformal field theories presumably have no moduli. They might have operators that are very close to marginal, but generically, you wouldn't expect exactly marginal operators. Good. Good question. Any other questions? Yeah, there's a question, is this related to 24 free bosons? Sorry, I'm just reading in the chat. It is. When I said it's constructed based on a torus, that's what I was referring to. So one way of constructing the monster CFT is you take 24 free bosons. You need to make them chiral bosons to get a chiral CFT. You take 24 free bosons and you put them on a lattice, and a specific 24-dimensional lattice known as the Leech lattice. And then you have to do an orbifold of that theory by Z2. That's the monster theory.
Thanks. Yes.
Yeah. Good. Okay, I see there's a few other questions, but it looks like as many answers in the chat as questions. Okay, there's a question, is the statement that these are the only smooth solutions with a single boundary T2, or even with any number of boundaries, these are the only solutions? The statement is that these are the only solutions with a single T2. If you've got many T2s, then you have disconnected sums of these. And I believe, and yes, in fact, if you have many T2s, the only solutions that you have are disconnected sums of these. That is to say, the unions of a bunches of handle bodies. Here, note, there's a subtlety in the math literature, because in the math literature, when people say a T2 boundary of a hyperbolic three-manifold, sometimes they mean a very large T2, but sometimes they mean a very small T2. And so if you look in the math literature, you'll see a different answer, but that's because what I mean is a very large T2, not a very small T2. Yeah. There's another question.
Yeah, I think that's me.
Okay, yeah.
Yeah, so you had mentioned that the study of these ECFTs for different values of C is related to just like different dimension lattices. Mm-hmm. So for C equals 24, which from what you were saying sounds like the easiest one to do.
Yeah, sorry, I misspoke. There's 24 lattices. There's 72 chiral CFTs. Sorry, I realized I misspoke earlier. Okay. There's 24 lattices known as the Niemeyer lattices. Yeah.
Okay. So is it that each lattice gives you a different ECFT?
Right. So the story, so the story is that a generic, I mean, we're getting into the weeds of chiral CFT here. The story is that a generic lattice will give you a partition function that has some number of states here. Okay. So that wouldn't be what we would call an ECFT. There's one particular lattice which has no, okay. I don't want to spend too much time on the lattice. This is related to problems in sphere packing and stuff like that. But roughly speaking, the Leech lattice is the lattice which has no vectors, the only even self-dual lattice in 24 dimensions, which has no vectors of length squared 2, which if you trace through the CFT analogy means no operators of dimension 1. And so because of that, that's the only lattice that you can start with and not get a constant term here. Okay. Right. Yeah. I think in the interest of time, I don't want to get too much into the weeds, except to say that there are a bunch of different lattices you could use to try and construct these CFTs. And if you want an extremal CFT, the monster is the one you're going to want to work with.
Thanks.
So let me suggest this is probably a good point to stop the recording.